Chapter's October meeting. We were going to be having a presentation on embedded tube rating systems today. We'd like to thank our chapter sponsors. To date for this 22-23 ASHRAE year, we are currently sponsored by both Train and McDonald Miller. Thank you so much for your support. If your company would like to sponsor the chapter as well, we would certainly be willing to work with you to get sponsorship as well. We have different sponsorship levels. If you'd like to know more, you could email president@pugetsoundashray.org. Moving on, as a general announcement, we are a voluntary organization. We are looking for volunteers for several committees as well as upcoming board positions. If you would have any interest in volunteering for the chapter, for a position, for a role on our board, again, please email president@pugetsoundashray.org and we would love to work with you. Upcoming events, we have a Top Golf event in Renton, October 27th. Additional details will be sent out in our monthly flyer going out shortly if it hasn't already. I believe it may have. And coming up next month on November 6th, we have an event for building tiny homes with Puget Sound ASHRAE. Moving on to our presentation, we have Devin with Uponor giving us a presentation on embedded tube radiant systems to maximize energy efficiency. So without further ado, Devin, I will stop sharing and you can start your presentation. Thank you so much for being here today.
Thank you, Rich. Appreciate it. So go ahead and share here. All right. So thank you, everyone, for joining online. It's a pleasure for me. It's an honor for me to be here with the Puget Sound chapter. This presentation, as had been mentioned, is being brought to you by through ASHRAE's Distinguished Lecturer Program. And this is a program that provides chapters such as yourselves access to a variety of different speakers and topics. This is something that we're always looking to improve. So I believe afterwards there will be an email that goes out with an evaluation form. And if you have some time, if you could please take some time to fill out that evaluation form, it'll help us as we continuously try to improve this program. The other thing I'd like to encourage you to do, if you're not already doing, is volunteering. And as Richard mentioned, ASHRAE is a volunteer organization of members serving members. And there are a lot of great opportunities to serve, whether it be at the chapter level, the regional level, or at society level. So it's tremendously rewarding. If you haven't already done it, I encourage you to get in touch with the chapter leadership there to get involved. From society standpoint, sometimes there's this tendency to think that a lot of the standards, the handbooks, the guidelines that we use on a day-to-day basis to best serve our clients are all developed by a group of people kind of tucked away back at headquarters in Peachtree Corners, Georgia. But the reality is that all of these standards, all of these resources that we use to really improve our industry are all developed by volunteer members like yourselves, all working together throughout the year, to improve our industry. And a lot of that work, the work takes place throughout the entire year, but we do get together twice a year for our conferences. We just had our annual conference in Toronto. And we've got our next conference is the 2023 Winter Conference, which will take place in early February in Atlanta. So great opportunity to go. You can check out ASHRAE's new global headquarters building, also participate in the AHR Expo to see all of the great new innovations that manufacturers are coming out with. So encourage you to, if you're not signed up, to try to make your way to Atlanta. But if you're not able to travel, there are still opportunities to get involved at, say, technical committees, and of course participate in the conference remotely through the virtual conference, excuse me. So that is all available on ASHRAE's website at ashrae.org. All right. I've had the opportunity to get involved for the past 25 plus years. It's been tremendously rewarding to be able to interact with other people within the industry, but also it's been rewarding for me because I've been able to meet just a lot of amazing people. So onto the topic. We're talking about energy efficient embedded tube radiant cooling systems, or using embedded tube systems to improve the energy efficiency of your project. And so before we get started, I do want to talk a little bit, just give you a little bit of background. So I work for a manufacturer. I've been doing that for about 13 years now, but prior to that, I spent about 15 years as a consulting engineer. So I was a managing principal of a consulting engineering firm down in San Diego, but I actually started as a mechanical designer in a firm over in Phoenix, Arizona. So I spent a good chunk of my early part of my career in Phoenix. And so, yes, I am an Arizona Cardinals fan. So you're welcome. I actually didn't even get the chance to watch Sunday's game because I was tied up with some other things. But usually, I usually like to watch the football games, and many of you on this call probably saw that game. So, okay. But anyway, when I'm watching a game, sometimes, there's often this tendency when we watch a football game to watch kind of where the ball's at, right? What the quarterback's doing, what the running back's doing, the wide receiver. But when I watch a game, I always like to focus on what's happening at that line of scrimmage, what's happening between the offensive and defensive lines, because whoever wins that battle is really going to be able to dictate the flow of the game. And I think that whole mentality, that idea of watching where the ball isn't, came to me from, of all places, my high school history teacher, who was also the offensive line coach for our football team. And he would often try to weave these stories about American history battles, and try to make analogies to football, in football terms. And I know that he would, I was talking to some of his players. Again, he's the offensive line coach, and he would make this statement. He would go in front of them and say, "Gentlemen, this is an important game. We need to win this game. It's all on you." And I can't help but think, I'm all for, these types of speeches, but I can't help but wonder what was going through the minds of those offensive linemen. What do you mean it's all on us? Have you ever felt that way? Have you ever felt like the success of a project that you're undertaking is squarely on your shoulders? It was about, gosh, close to 20 years ago now. I was sitting in my office in San Diego, and one of the other principals of the engineering firm I was working with came in and he said, "Hey, are you free tomorrow?" And I looked at my schedule. I said, "Yeah." And he said, "Okay, can you cover a meeting for us?" And for me. And I said, "Okay, that's fine." You see, our firm had been on one of three teams that had been shortlisted on a large scale design build project for a local community college project. And he needed me to cover on that project. And so I said, "Okay, give me the file and we'll go through it." And he said, "No, no, don't worry about it. I don't have time. Just go to the meeting, take good notes, and then we'll talk about it when we get back." So I said, "Okay, fine." So I went to the meeting, huge room, and you can see all the different parties, the contractors, the different subcontractors, the subconsultants, all kind of working throughout their plans on how they were going to win this project. And I found our team in the corner and I went over there, and then we watched as the facility manager for the campus got up in front of everyone and said, "This campus is committed to sustainable design. And so therefore, all new projects on our campus shall be minimum LEED Platinum." And we thought for a moment, how is that a minimum? And so, he came back and they said, "Okay, it was going to be LEED Silver, minimum LEED Silver." But it was clear to everyone in that room that if we wanted to wow that selection committee, if we wanted to win that project, we had to do everything we could to get that LEED Platinum. And so we went back to our corner, and the architect who was in charge of our design effort, he said, "Okay, who's the mechanical engineer?" And I kind of, I raised my hand, and he said, "Did you hear what he said? LEED Platinum. We need to win this project. It's all on you." And I couldn't help feel like one of those offensive linemen. The burden of the success of this project was squarely placed on my shoulders. And I started thinking, is that really fair? Why should the mechanical engineer have that burden? But if you think about it, and we all know, if you've been involved in lead projects before, you know that there's a lot that goes into it. And I certainly recognize that now, people are perhaps moving away from LEED, going to some other building standards, going to things like WELL, or really focusing on some of the other aspects of a building that lead to its sustainability and carbon neutrality. But when you start looking at LEED, let's start with that. You look at LEED and you look at, say, LEED 4.1, and you can look at all of the points that are available and how many of the points, the majority, a lot of points are right here, right? Energy and atmosphere. And if you look at all of the points that are available through this 4.1, then you can see that about a third of the points available can be directly impacted by the mechanical system. And so, yes, there's a lot that goes into LEED, but at the same time, the choice of the mechanical system, how effective that can be, has a great bearing on whether or not a project is able to achieve those higher levels of LEED. Now, we're not going to spend a lot of time, not much more time at least, talking about LEED, because of course there are a lot of different standards that people are using today, and we're seeing a shifting focus away from, say, energy efficiency, which Energy and Atmosphere is really focused on, moving towards really creating healthy, sustainable buildings, and really focusing on operational carbon and embodied carbon. But at the same time, you go back 10, 15 years, 20 years even, and you look at what LEED has done. Even though it may not have been, a perfect system, what it's done is it forced us at the time to really examine how we design buildings. How do we approach it? Are there different ways to design buildings? Can we do better? And it's made us really look at different ways that we can optimize the mechanical system in balance with the rest of the system, the building envelope, all the other systems, in such a way that we can truly create a sustainable, high performance building. So as members within the ASHRAE community, I'm sure that you've seen a lot of different presentations on different types of technologies that can help improve the overall energy efficiency and sustainability of a project. Today, we're going to focus on this one here, upper right-hand corner, radiant heating and cooling systems. And so here's a system where we're taking tubing, typically cross-linked polyethylene tubing, embedded into the concrete slab, and it's circulated throughout that concrete slab, and then it comes up to manifolds and such. And when we talk about radiant systems, oftentimes we think back to residential radiant, and that's certainly where radiant first got its roots here in the United States, at least. We look at residential radiant, you think of radiant heating, say in your basement. Maybe some of you have had that. But what we're seeing more and more of, as building owners, as engineers, as contractors start to better understand the opportunities for energy efficiency by incorporating this type of system, we're seeing more and more use on large-scale commercial projects. This project you may be familiar with is down in Northern California, Cupertino. It's a large-scale project, almost 3 million square feet of radiant heating and cooling. And so we're seeing more of that for a variety of different reasons. So that's what we want to cover today. We're going to cover just a handful of quick kind of subtopics. We'll start off with radiant fundamentals. How do these systems work? We'll then start looking at, from a practical standpoint, how are they built? What are the slab construction details? Where are these? How are these systems going to be actually designed and installed? We'll then go into some kind of strategic discussions on how we want to create a proper zoning plan, and then how we control, how we deal with the zones based on, piping and controls, and then finally wrap up with cost. So that's kind of the agenda for today's presentation. I believe we have a chat function. If questions come up, please utilize the chat function, and hopefully we'll have time at the end. We can open up mics and have a discussion. Okay, so let's talk with the first topic, and that is radiant fundamentals. What is the physics behind how these systems work, and how they differ from what we're typically used to, a conventional airside system? Well, one other thing to note is that radiant systems are not new. This idea of using radiation heat transfer is not new at all. As a matter of fact, if you go back hundreds of years ago, you can go,
once the floor is done.
We go back to the Korean Ondol system, and here's a system where you can see an elevated floor surface, and then you have a hot flue gases from a fire, from a stove, if you will. And those hot flue gases are circulated on the underside of that floor and then exhausted through the chimney. And that hot flue gas will actually warm that floor surface. And so I had the opportunity to go to Korea about 10 years ago or so, and got to see a mock-up of this type of system. And you can see here, this is where kind of the fuel would be put in, the wood for the fire would burn here, and then it would be circulated on the underside of that slab and then exhausted through these chimneys. And you can understand how, in a culture where people are very close to the ground, this made a lot of sense. And so we saw this throughout Asia. We also saw this in Europe. And you look at some of the Roman hypocausts that were built, these Roman bathhouses, very similarly, where you have this elevated floor surface, and then you've got hot flue gases being circulated on the underside to create these warm surfaces. And so that's kind of, the advent, if you will, of radiant heating systems. And now we want to kind of take that same principle of radiation heat transfer. And again, it's a little strange when we think about radiation in these terms, but how do we use it to cool? And historically, if we look at these being hundreds of years old, how old are radiant cooling systems? And the first radiant cooling system that I could find was something back in 1936, and this was the Jamoli department store. And so this was in Switzerland, they had a radiant heating system, but they were able to take advantage of a nearby river that had cool water, and they're able to circulate that cool water through that network to get a sense of radiant cooling. And so that was kind of the first one back in the 30s, but certainly now, we saw this picture earlier, we've got tubing that's embedded into a concrete slab, and then that tubing comes up to the manifolds. And by simply controlling the temperature and the flow, we're able to control the temperature of the slab itself and drive heat transfer in one direction or the other. So essentially, heat and cool by controlling the surface temperatures. Now, I'm often asked, Devin, radiant heating, it makes a lot of sense. We've got a floor and we're heating, but if we want to cool, doesn't it make more sense? Don't you have to do it from a ceiling orientation? And if I ask, why would you think that? The answer invariably is, well, come on, everybody knows heat rises, right? I think we all agree heat rises. Well, the reality is heat doesn't rise. Hot air rises, right? Hot air rises because of the differences in buoyancy, because of the density, and that causes it to rise. But if heat doesn't rise per se, what direction does heat go? And all we need to do, of course, is go back to our good friend, we all know from thermodynamics class, the second law of thermodynamics, or more specifically, the Clausius statement, or the second formulation of the second law of thermodynamics, that states that heat will always naturally go from a state of high to low, so from hot to cold. And I think intuitively we understand that. So if you've got two surfaces, if you've got two different temperatures, as long as you have that delta T, you're always naturally going to get an exchange of energy from high to low, regardless of whether or not it's coming from the floor, the ceilings, the walls. As long as there's that delta T, you're going to have that energy transfer. And so we're able to take advantage of that to create comfortable spaces, because at the end of the day, that's our main focus, right? Our main focus is to create these comfortable spaces so people can occupy them safely and comfortably. And if you look at human physiology and the way the human actually exchanges energy with the environment around us, a lot of it is done through, 48% almost, through radiation heat transfer. You can almost think of your skin as a radiant surface, and you're constantly exchanging energy with the space, with the objects around you, based on whatever that delta T is. You walk out on a cold day. I'm actually in Boise right now. I got off the airplane. To me, it was cold. It was in the 50s. And so, walk off, and there's a delta T between the air temperature and my skin temperature, and so that's going to cause the heat in my body to leave, and that loss of heat results in me feeling that cool sensation, and vice versa. You can see if you're absorbing heat, you're going to feel warmer, and it's all based on that delta T. And so we're able to use that as we focus on providing spaces, designing systems that lend themselves to thermal human comfort. But if we talk about thermal human comfort, what is the one standard that we all know and love? The one standard that we go to bed reading every night? It is, of course, ASHRAE Standard 55. thermal conditions for human for human comfort. And if you go through ASHRAE Standard 55, you know that there are a lot of different factors that impact thermal human comfort. And you can kind of put them together in these 6 factors. But as system designers, we really don't have much opportunity to really impact things like clothing and metabolism. Those are really functions of the space, the function within that space. And so as system designers, we really need to focus on these 4 topics. And I think by and large, we all understand the impact of air temperature and air movement on a person's comfort. Obviously, we all understand the importance of indoor relative humidity, not only from a comfort standpoint, but from a health standpoint. But it's that last term, radiant temperature, that sometimes causes people to pause to ask, well, what is that? What is the difference between radiant temperature and air temperature? Because again, when we talk about the systems that we're more conventionally used to designing, air-based systems, our entire focus is on, what is our discharge air temperature? What is the resultant mixed air temperature? We're all focused on air temperature as a means to determine comfort. We all think, oh, if it's 75 degrees, we're comfortable. If it's, maybe 70 or 68 in the winter, that's considered comfortable. But that's focusing just on air temperature. And what ASHRAE 55 recognizes is that a person's comfort level is not only due to air temperature, but also this last term, radiant temperature. So what is radiant temperature? Well, if you were to take a room and let's, think about the room that you're sitting in or standing in right now. And let's say you had a radiant, you're controlling the floor surface. Well, all of the other surfaces, the windows, the walls, the ceilings, those would be considered uncontrolled surfaces. So if you take the area weighted average of those uncontrolled surfaces, you would get an approximation for what is referred to as the AUST, or average uncontrolled surface temperature. Don't really get much out of that term. And so we take it the next step and we do incorporate into that same calculation the surface that we are controlling. And so if we have all of those surfaces, then we get an approximation for the mean radiant temperature. And that's a term we hear more often, right? Mean radiant temperature. It's the area weighted average of all of the surfaces around us. Now, to take it a next step further, if we were to average the mean radiant temperature with the air temperature, which we all know and love, well, then we would get an approximation for what's referred to as the operative temperature. And this is really key because if you go through ASHRAE Standard 55 and look at, say PMD, PPD curves, you're looking at those ranges which define what is considered, comfortable for most individuals, then what you're looking at is those charts, those graphs, are looking at not air temperature, but operative temperature, because operative temperature can be thought of as the temperature that the individual, that the body actually perceives. It's not the same as the air temperature. And so to kind of, put that in an example, I'll kind of use the example I gave earlier. Got off the plane in Boise. So I come out and the air temperature, I believe it was 51 degrees. So come out, I feel cold. It's 51 degrees. And then as I'm walking to the rental car, I'm walking through the sun. And now I'm getting that radiation energy, that radiant heat transfer from the sun. And all of a sudden, I don't feel as cold. I feel okay. So the air temperature is still 51. But because I'm getting that energy from the sun, I feel much warmer. And so it's not just the air temperature, it's the temperatures all around you that are going to impact whether you feel hot or cold. And so if we take those numbers and put them into an example like this is just kind of a make-believe room. So just hang with me for a second. Let's say that we've got this room and we're controlling the floor surface temperature. We're controlling that floor surface temperature to about 75 to 66 degrees. Well, if we have a room temperature of 78, we're controlling just the floor surfaces, and the room temperature 78, and then we've got all these other uncontrolled surfaces, the windows, the walls, the ceiling. We have, in this case, AUST of about 78, a mean radiant temperature of about 72, because we're taking into account that 66-degree floor slab. That would result in an operative temperature of 75. Well, what does that mean? It means that the individual within that space would feel like it's 75, even though the air temperature is being controlled to 78. And I saw that in a example here. Some of you may recognize this project. This is the city center more precisely, that picture is the Crystals Mall, which is part of the city center. It's an MGM complex on the Las Vegas Strip. So if you had the opportunity to go to the 2022 Winter Conference in Las Vegas, you may have seen this building. And what you may not know is that all of the public areas, areas like here where the public is walking through the mall, they're radiantly cooled. Okay, so I had an opportunity a number of years ago. I took a group of engineers to this facility, and we were walking through the mall. And I asked them, "How do you feel?" And everyone agreed they felt comfortable. You know, everyone felt fine. And I said, "Okay, if you had to guess the temperature within this space, what would you guess it to be?" Because as we all know, and I'm sure we all agree, engineers have a much keener sense of awareness when it comes to determining space temperatures. And so I polled them. And down the line, we went, and it ranged everywhere from 72 to about 75 degrees. So everyone agreed, that they were comfortable. And if they had to guess, it was about, at worst, maybe 75 degrees within that space. I looked at my space temperature sensor. It was 79 degrees. 79 degrees in that space. And you wouldn't think that you could design a space at 79 and have, people, be okay with that. People be comfortable. But you can imagine, I looked at the floor surface temperature with my temperature gun, and the floor surface temperature was 66. And you can imagine in a mall, the person's relationship to the surfaces around you, a lot of it is that floor surface. Most of it's that floor surface. And so we've got a floor surface at 66 degrees that's continuously drawing energy away from the body, leaving the individuals with that cooling sensation. So they feel much cooler than the air temperature actually is. And so that's one of the great benefits with radiant systems is we're able to maintain optimal levels of comfort at higher or lower set points. And typically with cooling, we try to maintain about a 78-degree space, with heating about a 68-degree space. And so you can imagine with a large volume space like this mall, the facility manager only having to manage that air temperature at 79 can yield tremendous energy savings, not having to drive it down to 74 or 75 degrees. Okay. Another benefit is direct solar heat gain. And I'm sure many of you have worked on projects like this, and I sort of shudder when I see this, because you can imagine you're running through a load calc. So you look at the room sensible and calculate the air needed to deal with that room sensible, that tremendous solar heat gain that can just really raise the demands on the HVAC system. Well, in this particular instance, and in many instances like that, they're able to effectively manage that direct solar heat gain because they have a radiantly cooled floor surface. Well, why is that? Well, take a look at what is happening with direct solar heat gain. You've got that shortwave radiation, the energy of the sun coming through the fenestration, and it hits the floor. And when it hits the floor, a couple things happen. Some of that energy is going to get absorbed by the floor based on the absorptivity of the floor. The rest of it is actually going to get converted to long wave radiation. And it's that long wave energy that's going to get reflected back into the space that's going to warm the objects and the bodies within that space. If we're cooling that floor surface, we're able to absorb a much greater percentage of that energy before it gets reflected back. And that's why you see a lot of radiantly cooled floor slabs in glass atriums, areas like that museum project, because they can effectively deal with it without having to have, a wind tunnel blowing air through there. Okay, so here's another picture of a project, headquarters building, where you can see they've got a large glass facade, but they're able to effectively manage that direct solar heat gain because of the radiant floor surface. And so there are a lot of different advantages to radiant cooled systems. We already talked about the high direct solar heat gain, superior human comfort, but then the fact that we're taking a lot of the load, we're dealing with it with the floor surface, which gives us that opportunity to reduce the ductwork. Right, so we're relying less on the airside system. We're always going to have to provide ventilation per code, and per ASHRAE standards. We always want to provide ventilation, but we're able to reduce the size of the airside system potentially, and that could give us greater architectural freedom. We have smaller ducts in ceiling spaces, and we can reduce some of the more common complaints with HVAC systems, drafts and noise, with the air side. But really what's driving the desire, that interest in using radiant systems, is energy efficiency. And that's, the topic today is how can we use radiant systems to maximize the energy efficiency of the building or reduce the energy use of a building. So you look at the different studies, and there are a lot of different studies. This one's a little bit dated, but this was Lawrence Berkeley National Lab studies, and it showed that a radiant cooled system, when used in conjunction with a dedicated outside air system to provide the code required ventilation, could save anywhere from 17 to 42% over the baseline VAV system. And they did studies throughout the country, all different climate zones. You can see a lot of that savings is right here, right? Is the fact that we're taking a lot of that fan motor horsepower that we were going to use to blow air through ductwork, and now we're providing a minimal amount of ventilation, latent capacity, of course, and we're taking a lot of that load through our radiant system. So we're circulating with pumps. And because we all know the heat transfer capacity of water, moving water, is so much greater than that of air, we're able to move those BTUs that much more effectively. And you look at some of the other studies that have been done. Pacific Northwest National Labs, which I'm sure many of you are very familiar with, did a study on, again, similarly showing that radiant cooling systems, when used in conjunction with a dedicated outside air system, could save about 50% over the baseline. And this was an older study, again, ASHRAE, based on ASHRAE 90.1 in 2004. NREL, National Renewable Energy Labs and Department of Energy, working with ASHRAE on advanced energy design guides, which hopefully you're all using, looked at different types of buildings, different types of climate zones, and showed that in every single climate zone that 50% energy savings, and that's what they were focusing at the time, could be achieved using radiant cooling systems. And then we go to some of the other studies that have been done. You look at AIA, the 2030 challenge, and we look at, the 50 to 50, 50 strategies for high performance buildings. And that was initially came up with years ago, 50 strategies to reduce energy usage by at least 50%. And from a lot of the stuff is very common, things like proper maintenance, proper commissioning. But really, there were two specific HVAC system strategies that they talked about, and they were radiant heating and cooling and geothermal systems. And so we see acknowledgement, but really, it's nice to see those studies. But really, what we want to look at are, where has it actually been used? What are the case studies? What are the actual projects where this has been implemented? And we see projects like Bangkok Airport, where they had 30% energy savings over the baseline VAV system. Ideas Z Squared facility, LEED Platinum. Western Science Center, LEED Platinum. Cooper Union, LEED Platinum. NREL Research Support Facility and David Brower Center, LEED Platinum projects. Manitoba Hydro Place in Winnipeg, Manitoba, called one of the most energy efficient office buildings in North America, also LEED Platinum. And then, of course, Clemson University, Lee Hall. And I want to pause for a second. I don't want anyone to get the wrong impression. If you've worked on LEED projects, if you're working on LEED projects now, you know that there's a lot that goes into it. Okay. We talked about it a little bit in the beginning, but, and I'm not at all suggesting that you design a radiant system and you check a box and you get LEED Platinum, because you all know there's way more to that. But these are all examples when posed with that challenge, the design team was able to incorporate radiant heating and cooling as part of a complete energy efficiency design strategy to get that highest rating achievable by the USGBC. And so it's something, you look at some of the other studies that have been done. California Energy Commission recently had a large-scale study on radiant systems, because they found that over 50% of their net zero projects utilized a radiant strategy. So you look at a lot of these different projects from around the world, around the country, and you look at something like Clemson Lee Hall, in South Carolina. And this was actually the subject of an ASHRAE High Performance Building Magazine case study. And they showed that radiant systems could be very effective even in areas where you have high humidity. So you think of South Carolina. And you think of the humidity there. And there's often this idea that radiant cooling cannot be incorporated in a high humidity environment. But here's a project where they were able to successfully install it. And they actually also have operable windows, openable windows, because they realize that, if it is hot and humid, people close windows. But they haven't had any issues with surface condensation. Another case study, again, this one is quite a few years old. It was originally installed over 10 years ago. excuse me, is the Infosys project in Hyderabad, India. And this was a really interesting case study because Infosys is a tech company in India, and they wanted to look at how they can improve the energy efficiency of their building stock. India is going through tremendous amount of growth right now, and that's one of the key challenges is how are they going to deal with it with the existing infrastructure that they have. So they need to find ways to be as energy efficient as possible. And so they designed this new building, and they did it sort of as a study. They took half the building and designed a VAV system, a conventional VAV system, and then the other half they designed a radiant heating and cooling system. And then they monitored it. And what they found is they had an optimized VAV system, and the VAV system performed about 30% better than their existing building stock. The radiant system, performed about 32% better than the VAV side. So it performed better from an energy efficiency standpoint. It provided a higher degree of thermal human comfort and satisfaction for the building occupants, and it was done at a lower capital cost. And so this was a great case study that really shows the effectiveness and the viability of a radiant system in areas that are not just lobbies or wide open areas, but actually in office spaces. And so continue to see more and more of that when we start looking at the performance of the system. And these are just rules of thumb. And I sort of hesitate to show these because they can vary so widely. But again, take this as a rule of thumb. A radiant cooling system, first off, and I sort of alluded to it earlier, is only going to deal with your sensible load. Okay. You're running our load calcs. We've got sensible, we've got latent. Well, we can't touch the latent. Why? Because if we touch the latent, obviously that's going to result in that phase change, that surface condensation. And the last thing we want is to have wet floors or wet ceilings. And so we're limiting ourselves to the sensible. So we are going to need a secondary system. We're going to need that DOAS system anyway for our ventilation. And so we're going to use that for latent capacity as well. And so from a floor cooling standpoint, about 12 to 14 BTU per square foot is what you typically will expect to see. It's really a function of what your delta T is between your surface temperature and your space temperature. And there are a lot of variables that will go into that, particularly flooring. With a ceiling, you can get quite a bit more capacity, about double. And I'm kind of chuckling now because at the onset, I made the comment, it doesn't matter if it's a floor, a ceiling, a wall, it's still going to work because second law of thermodynamics. And it is still going to work, but you can get more capacity if the system is oriented in the ceiling because you get the convection. You get that convection, you get that natural, the cool air dropping. And so it's a combination of convection and radiation. And so you are going to get more capacity out of that. The other reason why a ceiling can also provide that much more capacity is, as I just mentioned, the capacity of the system is going to be a function of the delta T between the surface temperature and the space temperature. And one of the constraints that we have on a floor surface, and this is per ASHRAE 55, is we don't want the floor surface to be too cold, right? Usually about 66 degrees because no one wants to walk on that cold surface. We like walking on warm surfaces. We get that toasty feet kind of feeling. But we don't want it to be too cold. And so we're going to limit our floor surface to about 66. Well, last I checked, no one is walking on the ceiling. So it gives us that opportunity to be a little bit more aggressive with our surface temperature dew point permitting. And so we can see surface temperatures that are on the 62 degree range versus the 66 that you normally want to maintain on a floor surface. And that's why you can get much more capacity out of the ceiling. When you've got direct solar heat gain, as we showed with that museum project, all of that glazing, equally, we can get quite a bit more capacity because we're absorbing a lot of that shortwave radiation before it has a chance to reflect into that space. From a system parameter standpoint, how are we designing the systems? Again, I hesitate to show this because it varies widely, but you can take this as sort of rules of thumb. Rules of thumb, the tubing is laid out on the floor slab. Typically, the industry has gone to cross-linked polyethylene or PEX. I know that when I designed my first system as a design engineer, I used a boilerplate specification and used copper tubing, which was just a disaster for the contractor trying to make those bends without kinking it. And so because of that, the industry has gone to polymer solutions like PEX. And so Different diameters. 5/8 is typical, more typical for a commercial application. 6 to 9 inch on center spacing for cooling. For heating, you can get into the 9, 12, 18 inch on center spacing. And then your typical loop length is about 350 to 500. All of this is really dictated by our flow rates. Okay. So we know our load, say 12 to 14 BTU per square foot. We can run hydronic calculations to determine what our flow rate is based on the delta T. And typically on a cooling system, we're looking to maintain delta T's on the order of 5 to 8 degrees. With heating systems, we can go, 10 to 20 degrees, but with cooling, we try to maintain about a 5 to 8 degrees. So our GPM is going to go up. And so what we're trying to do when we look at tubing diameter, when we look at tubing loop length, is we're trying to make sure that our pressure drops are manageable. The last thing we want to do is try to design a energy efficient system and then have to oversize our pumps to overcome the pressure drop within that network of tubing. And so that's why we usually gravitate towards that 5/8 inch tubing. So and then we see that minimum surface temperature per ASHRAE 755 at 66 degrees. Okay, so when we only need, say, 55 degrees, I skipped that part. Our water temperatures are not 42 to 45 degrees. We're looking at 55 to 58 degrees because we don't want to overcool that slab. We don't want that 66 degree slab to drop any cooler. So depending on the floor makeup, depending on your flooring, you can usually get away with temperatures that are on the order of about 55 to 58 degrees. And so that opens up different opportunities. This is a project in San Francisco, the Pier 15 Exploratorium, where they were able to take advantage of the fact that they're right there on the ocean, right? And so they were able to take ocean water that about 9 months out of the year was about 55 to 58 degrees, go through a filtration tank and through a heat exchanger, and they were able to get essentially free cooling for about 9 months out of the year. And then in the summer months, they would use that water to supplement or to kind of to feed the heat pump system. And so different opportunities to really save on the energy. Okay, so that's on the fundamentals. When it comes to slab and construction details, a lot of different ways to do it. If you've done radiant heating systems before, then you know that these are going to look very familiar. We've got typically slab on grade, you've got an insulation layer, and then the tubing is just secured to with wire ties or zip ties to either the rebar or a non-structural wire mesh. Similarly with a suspended deck, the main difference being that insulation, that thermal break on the underside of the deck. What we see much more, as being much more prevalent here in North America particularly, is the use of a topping slab, where the tubing is actually installed in a secondary slab. Now, I'm talking to a lot of engineers now who are trying to get away with that because we're trying to actually reduce the amount of concrete within the space because of the embodied carbon of cement. And so we're seeing sort of a move away from topping slabs, but we are seeing still it being used pretty regularly. And so here we have a topping slab, usually a lower mass slab, 2 to 3 inches, and then the thermal break, usually 2-inch polystyrene insulation, and then the suspended deck. So the topping slab is going to be a little bit more responsive. We'll talk about controllability in a minute. And then, wood deck with gypcrete, a lot of different ways to do that. And so here you see a manifold, and this is eight loops. You can see, you can kind of count the 8 heads there. We've got supply in the bottom, loop goes through, return on the top. And so 8 loops. And if we said that each loop is, say, 500 feet, 8 loops, 500 feet, that's, I gotta do math real quick, 4,000 linear feet of tubing. Assuming that all of the tubing is within that space, at 6-inch on center, that manifold would take care of the space that's about 2,000 square feet. Not a lot, right? And so it's important that it's coordinated. There are going to be spaces, large spaces, that need multiple manifolds. And so as you're designing this, as you're coordinating with the architect, you need to make sure that you've got good locations for the manifolds. You ideally want to locate the manifolds as close to the zone that they're serving, because you don't want to run these long extended leaders, or you'd run out of that 500 feet. So here's an example that works generally well. You can see the manifolds are located close to the spot place they're serving. You don't, ideally they'd be in the space, because that leader, let's say that leader's 50 feet. Well, you just lost 100 feet supply and return of your total 500 feet. And so now there are going to be situations where if you do this, now instead of 3 manifolds, now you need 4. or you need larger manifolds, and that just increases the cost and decreases the operational efficiency of the system. Okay, so that was a very quick on slab and construction details. From a zoning standpoint, I guess the one thing I would say is we don't want to go too crazy with zoning. I think a lot of times we think of VAV systems, we think of an infinite amount of zones based on how many VAV boxes you have. Well, with a radiant slab, slabs are going to be very much slower to react. And so from a control standpoint, we typically will have, what's called water temperature zones where we're controlling to a specific water temperature, and you can have, say, 4 water temperature zones, and then within each zone you can have local zones where you're actually controlling flow. So in one case you can control your temperature, reset your water temperature based on the loads, and then you can basically turn flow off and on based on what the demand is within that space. I'll say that most of the time, and think back when you're designing your fan coil unit system, you usually only have one water temperature. So using local zoning or controlling with flow is typically a more common way to do that. But again, from a zoning perspective, oftentimes what we do is we have large radiant zones, and then we trim the load. If we have, say, small offices or such, we can trim the load with our VAV systems as long as they're both on the same mode of operation. We don't want heating and cooling systems simultaneously going at the same time. Piping and controls. So I'm sure that, as engineers, you have a lot of different ways that you can do your piping controls. When it comes to radiant systems, if you've got a single mode of operation system, like a radiant cooling only, radiant heating only system, it's relatively straightforward. You can treat it almost like a coil detail that you might have. But when it gets tricky is when you have combination radiant cooling systems. And so there are a couple different ways to do it. This is a switchover system. And so you can see across the top, you've got your 4-pipe system. And you're going to set the supplies and returns are going to a set of diverting valves. And it's important to note these are diverting valves, they're not mixing valves. We never want to mix chilled water and heating hot water. Just don't do that. We all know why, but don't do that. And so we're diverting. And it's specified as a diverting valve because you want to make sure that it's going to open and close 100% to each designated port. And so depending on the mode of operation, it's going to go 100% open to, say, chilled water supply, 100% open to chilled water return. And then that goes to the radiant loop. And then you've got, say, a 3-way mixing valve to actually make your design temperature. This shows one manifold. So don't think that you have to reset water temperature on the manifold level. This could be all the manifolds within that water temperature zone. Another way to do it, which we're seeing become more and more common, is an injection system. And so you can see here, again, 4-pipe system across the top, but then what we have are a set of valves or sometimes pumps that are going to inject small amounts of chilled water or heating hot water into the loop to create whatever your target supply water temperature needs to be. Now, it's important, you're not, similarly to what I said before, you're not going to inject chilled water and heating hot water simultaneously. You need to ensure that your control sequence locks out one set of valves at a time so that you're only doing it, only chilled water or heating hot water at the same time. And then you've got your circulating pumps to all of the manifolds within that water temperature zone. You can put a heat exchanger across one side, and that will ensure that you're not mixing chilled water and heating hot water over the course of a heating cooling season, in case the facility manager is managing chemicals differently. From a control standpoint, there are a lot of different points you want to control, and sometimes you look at this list and it seems overly complex, and sometimes you hear this comment that radiant systems are difficult to control. But the reality is with the exception of slab temperature, these are likely all points that you're going to be monitoring anyways on a high performance building. So those are points. From a cooling strategy standpoint, I've got a whole another presentation just on control strategies and on how to control the systems. But generally speaking, one of the more common strategies is to base load with your radiant system, get as much capacity as you can, and then use your secondary system that's going to provide your secondary sensible, your latent capacity to sort of trim the load. So you kind of using that secondary system, your airside system, as an offset to your set points. So you've got your two different set points. And then obviously you're continuously monitoring indoor relative humidity to avoid any condensation. And now we're going to talk about condensation now that we've got 9 minutes left. So sometimes, people talk about radiant cooling systems and their immediate concern is, what are you going to do when it condenses? Because there's this natural thought that it's going to condense. And when I started looking through this years and years ago, I found this very interesting quote. This is from Dr. Frederick Kasicki, Texas A&M University, and he has this quote. A lot of words, don't read that. Basically, what he's saying is that, we've been using radiant cooling successfully in Switzerland for over 15 years, but here in the United States, in America, there's this idea that you're going to get condensation. And when I first heard that, I thought, well, that's true, but we tend to be, agree or disagree, a bit more litigious here in the United States. And certainly as we look at what our responsibility is as engineers, not just in the US, but throughout, our responsibility as engineers is to safeguard the public. Code of ethics, number one canon in the Code of Ethics is to ensure that we're providing systems that don't put the public in harm's way. And so we want to make sure that we're designing systems that don't have slippery floors or aren't, creating moisture issues. And so it is prudent design to be wary of this. But the reason I thought this quote was a bit humorous is because he wrote this in his book on radiant cooling in 1946. So we've known for years, we've known for decades that this is potentially an issue, but what's changed? What's changed is as an industry, we have a much better understanding of how these systems work. And more importantly, we have controls, right? We've got the sensors, we've got the controls that can effectively monitor indoor relative humidity, calculate dew point, and then move valves accordingly to ensure that our supply water temperatures and our slab never gets to that where we're at risk for surface condensation. And so basic strategy, we all know condensation has a potential of occurring if our surface gets close to dew point. And so we always want to continuously monitor that. And so, we think back at what our typical design parameter is. And I said before, for a cooling system, we typically target a 78 degrees space temperature. 78 space temperature at what? 50% relative humidity? I'm sure all of you have your psych charts now, so look it up. If you pull out your psych chart or pull up a psych chart app, you'll see that what's your dew point? It's about 58 degrees. So what that means is any surface that's going to be close to 58 degrees is at risk for surface condensation. Well, what did I say before is what is our minimum floor surface temperature per 55? It's going to be about 66 degrees. Ceiling a little bit more aggressive, but still we're a ways away from ever putting ourselves at risk for surface condensation. So unless a valve sticks or controls go haywire, we really don't have a concern about surface condensation. Okay, from a controllability standpoint, there's this idea that a high thermal mass takes a long time to react. The reality is it takes a long time to react. And so that's why it's important that your control strategy is such that you're able to take advantage of the fact that not only does it take a long time for it to react, but it also takes a lot of load to change the temperature of that slab. So that's one of the great things about a high mass systems is once you've got it dialed in, it essentially creates this, this uniformity and evens out the fluctuations in internal temperatures and internal heat gains. And then you use your secondary systems to deal with your high low densities. Okay, so in the 5 minutes we have left, we'll talk just briefly about costs. And this is kind of my least favorite part of the presentation because it varies. It varies so widely. You look at the typical cost factors. There are things that no cost. There are things that are additional costs, obviously, especially if you're going to pour additional concrete. But there are opportunities to reduce costs, and there certainly is reduced maintenance costs. And so when we start talking about what are the costs, everyone always wants it to be in terms of dollars per square foot. But the reality is it really varies specifically based on the level of experience that an installing contractor has. I've seen areas, you look at some of the cost data that's been done, 10 to 12, I think that's very low. This is from 2021. Cost data says about 14 to 16 per square foot. I still think that's a bit low as well. I've seen projects, where the premium on it is probably on the order of $25 per square foot, somewhere around that range. Don't quote me on that. But we are seeing opportunities as contractors become more and more used to installing these systems, we're seeing that number go down quite a bit. And then we're also seeing manufacturers come out with different types of innovations like this rollout mat that can really help improve the overall efficiency of that installation. This particular solution can reduce the installation time, cut it by about 6 to 8 times faster. All right, so I've been rambling on for a better part of an hour now, but in summary, from a benefit standpoint, yes, radiant heating and cooling systems can be used to dramatically reduce the energy usage within a building and therefore reduce the operational carbon of a facility, providing superior thermal human comfort and improved architectural freedom. From a performance standpoint, you want to think in terms of about 12 to 14 BTU per square foot, about double that if you've got direct solar heat gain or if you're using a radiant ceiling orientation. And then important things to consider is make sure that you've got an envelope where you can effectively control the indoor relative humidity so we don't run into dew point issues. Pay a lot of, pay attention to controls. Make sure you've got a fine, you've written out your sequence of operations, and then make sure that the installation methods and the details of the flooring, the slab construction is all properly coordinated with the architect and the structural engineer. All right, so that's all I have for today. So at this point, I guess I'll open it up to any questions if anyone has got questions. Let's see, I don't see any questions in the chat. So I'm not sure if anyone wants to just unmute themselves or enter anything in the chat. Anyone? Oh, thank you, Dana. Appreciate that. One of the things that comes up is we talk about how we're designing buildings today, right? And what we need to do to ensure that we're designing buildings that provide a safe environment for the public. And one of the things that people have often said, one of the initial strategies that some engineers and facility managers were doing were, okay, we've got airborne infectious diseases, we've got COVID, we're trying to deal with that. What do we do with our ventilation? And they said, oh, let's triple the ventilation. Well, we know that's not the right approach. We want to make sure that we provide the right amount of ventilation. And that's one of the great things with the radiant systems. We're actually decoupling our sensible system from our ventilation, ensuring that we can always provide the right amount of ventilation while providing the right amount of heating and cooling. So I did see something pop in the chat. What kind of materials are you seeing being used for ceiling applications? Okay, so there are a lot of different great applications in ceilings. We talked about concrete slabs, slabs for the floor. Well, a lot of the projects that I showed you, the NREL Research Support Facility, David Brower Center, it's actually an exposed concrete ceiling. And so that's an opportunity, to have an exposed concrete ceiling. So it's similar construction method with the embedded tubing. You do want to make sure that you want to involve your acoustic engineer, your sound engineer, because once you have exposed surfaces like that you can run into issues with acoustics. But there are also a lot of other products available. There are radiant ceiling panels made by different manufacturers, some that even drop right into a ceiling grid. If you go to ASHRAE's new global headquarters building in Peachtree Corners, Georgia, they actually utilize a radiant ceiling panel system. And so oftentimes those are metallic systems, kind of a metal ceiling panel with tubing, and then the chilled water goes through there. And again, similar discussion, you need to make sure that you're monitoring your indoor relative humidity so you don't get rain in that space. Low mass applications. Okay, so I think we kind of covered both. Capillary ceiling panel, similar. So a capillary system's got the very small diameter tubing, typically embedded into like a JIT product or a kind of panel that very similar that can be installed in the ceiling and provide you with that high degree of cooling capacity. You just want to be very, very careful with your dew point. So, okay, so if anyone has any other questions, you should have my email address. Please feel free to reach out. Happy to answer any questions. Ooh, real quick. I know it's 1 o'clock, so if people have to drop off, I want to be very respectful of people's times, but I'm happy to stay on. There's a question here. Thoughts on eliminating the topping slab? In Europe, reportedly steel tubing is used for hydronic tubing. the steel tubing is used for hydronic, and the tubing is the steel reinforcement. Oh, interesting. So, talking about using the steel tubing as the steel reinforcement, haven't really seen that here in the U.S. Um, in Europe, the use of topping slabs is not as prevalent. They're used to putting the tubing in that large high mass slab because they take more of a, you may have heard like a tabs approach, thermally activated building system, where you're actually using the entire building, that slab, to heat and cool throughout, throughout the day. I think in the U.S. we tend to feel more comfortable with low mass slabs or even low mass concrete topping slabs because we feel like we've got a higher degree of controllability. The reality is they both take a long time to react. So we are seeing more and more use of kind of that high mass use within a in without the topping slab. The other thing to consider, it'll be interesting to see how the building industry reacts to, the call to reduce the amount of concrete, well, the cement in general. We are seeing innovations in low carbon concrete mixes. We are also seeing higher use of mass timber in these applications, and so had the opportunity to work on some mass timber projects where they have a very lightweight slab for the radiant. All right. So I'm past time now, so I'll go ahead and stop talking. But again, if anyone has any questions, please don't hesitate to reach out. It's been an honor. It's been a pleasure to speak with you this afternoon, and hopefully I'll be able to see you again soon. So thank you very much.
Excellent. Devin, thank you so much for the presentation. This was so great, and I'm sure everyone's really appreciative of it. Thank you for taking your time. Just one more closing remark before we end the meeting. Just a reminder that we will be sending out an electronic survey for today's presentation. Devin is a distinguished lecturer, and it is appreciative if you could fill out that form and turn it in. So I believe that's it. If no one else has anything further, I will officially close the meeting, and thanks everyone for attending. I'll see everyone in November. Thank you so much.
Thank you, everyone. Take care.